This video is the second part of a video in which we were explaining how pressure affects the freezing and the boiling point of water. In that prior video, we actually saw that when you increase the pressure in water, the freezing point goes down. That means that you can get liquid water at temperatures below 0 Celsius if the pressure is higher than 1 bar. And we understand that that's interesting in things like ice skating and glacier dynamics and situations where you have ice or cold water at high pressures. Right, what about the boiling point though? What happens to the boiling point when you increase the pressure? Well, the boiling point goes up. And the question is, do we have any instance of this type of behavior in the natural world? And the answer is probably, but that's is hard to figure out, right? Because sure, you can have liquid water at high pressures, maybe underground, but we never get a chance to see that. We can do this though with a man-made device like a pressure cooker. And actually this is the effect that pressure cookers use. All right, so what is a pressure cooker? Well, a pressure cooker is just a pot in which you're going to be boiling water, but you're going to lock it to make it constant volume. And because the gas that you're generating can't go anywhere, means that there's going to be a pressure build-up inside that pressure cooker. That's why it's called pressure cooker. Now, when you increase the pressure then, what happens is that the boiling point of water is going to go above 100 Celsius, which is the boiling point at 1 bar. Okay, and what that means is that you can get liquid water past 100 Celsius, maybe like 110, 120, and so forth. And this is very advantageous for cooking because now you have a liquid in which you can cook beans or whatever you want to cook, but the amount of energy that is stored in the liquid is higher than the amount of energy that you could get if you were boiling this open to the atmosphere at 1 bar, right? Because you can have liquid water hotter than 120, than 100 Celsius, then that means you're going to be able to cook food faster. Okay, so your beans, instead of taking 1 hour to cook, which is the time that it would take more or less when you're boiling water in an open atmosphere, in an open pot at 1 bar of pressure, now if you have more pressure, cooking the beans will take place in maybe 20 minutes, again, because you can have liquid water hotter. Okay? All right, so this is what happens to water when you increase the pressure, but it's also quite interesting to analyze what happens to the freezing and boiling points water when you decrease the pressure. Okay, so let's see how we would draw those graphs. Okay, I'm going to go reasonably fast here because we already know how these graphs look like. All right, so that is going to be the line of the gas. Then we're going to draw the line of the liquid and the solid at the reference pressure, which is going to be 1 bar for our case. That will be the liquid, and then this is the solid. All right, so what we have here is that this is not going to work. Let me actually erase this and draw it more cleanly. All right, so we have that would be the solid, this is the liquid, and this is the gas. That's going to work much better. Okay, and then again, the slopes of each one of those lines, we understand from this expression that are going to be equal to the minus molar entropy. That's why they're negative. And then we want to calculate what happens when you decrease the pressure. Okay, so we're going to draw these lines at a pressure P2, which is smaller than the pressure P1. So here we would be applying a vacuum so that the external pressure is not 1 bar, but something less. Okay, so let's see what happens here. All right, you take any point in the graph and then see what happens to the molar Gibbs energy when you change the pressure. In this case, you decrease it. Right, so when you make this negative, you decrease the pressure, because that's a positive number, then this should decrease as well. And the decrease is going to be proportional to the molar volume. Okay, so for the gas, we're going to say have a large offset for each point on this line, and again, that is going to be the line, that is going to be more or less like this. Okay, we can actually draw a little bit more offset, just for added clarity, like that. All right, great. Right, what about the lines of the liquid and the solid? Okay, so here you also are going to have that these lines are offset to lower values of the molar Gibbs energy because we are decreasing the pressure. But again, notice that water is special, right? So the offset, that's not a gas, that's a solid. Because the offset of the solid, the molar volume of the solid is greater than the molar volume of the liquid. Okay, so then that offset can be drawn like this. Okay, for the solid. And this offset is going to be drawn like that for the liquid. Okay, and again, notice that the offset for the solid is greater than that for the liquid, because the molar volume of the solid is greater than the molar volume of the liquid for only water. Okay, so what happens to the freezing point and the boiling points? All right, the original boiling point is right there. Okay, and the original freezing point is right here. Okay, so what are the new boiling points and freezing points? Well, the new boiling point, notice that is going to be the intersection of the gas line with the liquid line. All right, so that will be your new boiling point. And this is going to be your new freezing point. Okay, your fusion point. Okay, so what we see is that when you decrease the pressure, then the boiling point gets depressed and the freezing point goes up. Okay, so what consequences does this have in the natural world? Well, where do we get pressures lower than 1 bar? This is actually not hard to do. What you can do is just go up in the atmosphere, and then the pressure becomes increasingly smaller. So that people that live in really high countries like Bhutan, Bolivia, or Nepal, the Himalayas, for example, they actually have the pressure is much lower. I think that at the top of the Everest, the pressure is about 40% smaller than it is at sea level. Okay, so what happens there is that it's kind of a double whammy for the people who live in those countries for the following reason. Notice that now water is going to boil at less than 100 Celsius. Okay, so you can have that water might boil at 80, 90 Celsius. So if you're trying to cook with water, you're trying to boil something, then the cooking time is going to take longer because the water that you're utilizing is boiling at 80 Celsius, not at 100 Celsius. There's less energy in that water, and that means that your food is going to take longer to cook. Okay? The second part of the double whammy is that the freezing point goes up. That means that you can have solid water, okay, at temperatures higher than 0 Celsius. All right, and that means that you're going to have ice in the streets, for example, at temperatures above 0 Celsius. That means that they will see much more ice than what we see when the pressure is higher, like 1 bar. Okay, so this kind of concludes our discussion of how the molar Gibbs energy gets affected by pressure and temperature. We can close up by reminding what happens with water. Okay, for water, when you increase the pressure, the boiling point goes up and the freezing point goes down. But when you decrease the pressure, the boiling point goes down and the freezing point goes up.